And welcome back, Mindsetters. I hope you had a nice little break there and you did not disappear or go anywhere too far away from the TV. Hope you're now back, ready with your pens and pads out and ready to make notes. Because on that note, this is when I'm going to hand over to Phil, who's going to do a little experiment. So, Phil, what do we have there?
Okay, well, what I'm going to be doing here is I'm just going to be showing you the two different states of iron. What we're going to do later on is we're going to change one into the other. So what I've got on the right-hand side here is I've actually got a little bit of some iron 3. What I've done is I've made sure that I've got some pellets that you can actually see a very nice color. You can see that sort of very strong orange color that it's actually got. Now this is iron 3. Now this is iron 3 chloride. The reason that I've chosen it is because it's actually got a slightly gentler color, and you can actually see the iron 3's color on its own. Now on the right hand side is what we want, and that is iron powder. Now I need iron on its own to actually make implements like this. So if I want to make something like this, I've got to change something that looks like that into something which looks like this. And that's a little bit of a problem. I've got to convince iron 3 plus that it actually wants to become an element again. And that's quite difficult. That's where redox chemistry actually comes into play. So now when I want to take this iron 3 and I want to change it into an implement, the question is, how do the mines actually do it? Well, before the break, I actually showed you that the iron 3 is gotten from or extracted from that iron ore, that hematite. So what we're going to do is we're going to take the hematite now and change it into iron. So let's actually go through to the board and let's see how we can actually do this. So before the break, what I showed you was that open cast mining, that orange material inside there, is one of the ways that we actually dig up iron from the ground. So now this open pit mining was the way that I got the iron 3 plus iron ore, and I actually took this material straight out of that open pit, and now I've got to change it into something much more useful. I've got to change this now into iron, the element, and that's where redox comes in. So let's start with this. Now, iron is transformed by something which is called a blast furnace. So now I can take either one of my minerals. I can take Fe2O3. Remember that was called hematite. So if you're writing notes, just remember that that is hematite, or magnetite, which is Fe3O4. Now I'm going to make a couple of notes on this diagram. Now this thing is called a blast furnace. So a blast furnace is the most common way that we can change iron ore back into iron, the element. So let's take a look at what goes on inside a blast furnace. Now, into the top here, you can actually see those two little train pieces. And what they're delivering is actually two very important pieces. The two very important components that I put inside are iron ore, so that's going to supply us with the Fe, and coke. Now, this is not coke which you drink. What this is a very, very pure form of coal. Coke is actually a very, very pure form of carbon. Now you can get coke from coal. What they do to make coke is they heat up coal to a very high temperature to get rid of any extra pieces, and that leaves behind very, very pure carbon. It's kind of like a spongy material, but coke and iron ore is the stuff which they put inside the top of a blast furnace. Now the reason it's called a blast furnace is because I put this very, very hot gas which goes inside there. Doesn't look like the degree sign has come through very nicely. So what we're actually going to say is that that is degrees. Let's draw it in. There we go. So we've got degrees Celsius, which is 1,400 degrees. Very, very hot stuff. Now the reason that we need that type of temperature is to get the molten iron out of the bottom. Molten iron only melts at that sort of temperature, and I've got to make sure that that iron is going to stay liquid in order to do something useful for it. When I melt iron, it's going to move into something, and this is where we can actually start to change it. Now, this is where I want to bring up the idea of steel. So now inside here, you've got a whole bunch of carbon, you've got a whole bunch of iron. What we've got to do with the two is realize that they're going to get mixed up together. There's actually too much carbon inside this iron at the moment. Right, that is called pig iron. So if you actually want to do some notes on top of there, molten iron, which comes out of here, is called pig iron. The reason it's called pig iron has got nothing to do with the animal. It's actually got to do with the containers which it goes into, and those are called railway pigs. So pig iron is the iron which gets poured inside those crude containers. Pig iron has got way too much carbon. We actually need to reduce the amount of carbon inside there before we can actually change this into a usable form of steel. So at the moment, we've got Fe and we've got carbon, and the mixture of those two together is called steel. So when I mix those two together, I make an alloy which I call steel. And that's the steel which you and I know. Now, that's not exactly the same as the steel which I find inside a knife like the one I showed you earlier. I can always mix other elements inside this. I can mix in some silicon, I can mix in some chromium, I can start to mix in even metals which are like vanadium. Now you might have wondered, when am I going to ever use these elements? Well, those elements are very useful to mix with iron because it actually gives iron different properties. For instance, if I mix iron with chromium, that makes stainless steel. That's steel which doesn't rust, and that's quite useful. Because one of the biggest problems with just normal steel or mild steel is that if I leave it outside, if I leave it in water, it's going to rust incredibly quickly because carbon doesn't protect iron very well. So what I'm going to do is I can mix it up with a whole bunch of silicon or vanadium or chromium. So what we can do is we can add in all sorts of other elements. And that changes the properties of the steel. So we can mix in some silicon if we like, we can mix in some chromium, we can mix in all sorts of things, even vanadium. If you go find a spanner inside a tool shop, very often it says vanadium steel. And that means that we've mixed in the element V for vanadium. And that's a very useful element. So you can mix in any one of these symbols, or mix in any one of these elements rather, and make different types of steel. Now that changes the properties of those steel. Okay, but what I'm going to do is I'm actually going to focus on this reaction inside the blast furnace for a second, and let's take a little bit of a closer look as to see what happens inside there. Okay, well, let's just take a look at the balanced chemical equation of what's happening inside the blast furnace. Well, the basic idea is that I've taken my hematite, I've taken my coke, and I'm producing the iron, and I'm producing carbon dioxide. So I'm going to make a few notes as we go through this. Okay, so here is my iron ore. So there's the iron ore over there, and that is the raw material. That's the stuff that I want to change into steel itself. Over here, if you were listening carefully, the carbon itself is called coke, and that's a very pure form of carbon. Now what comes out, this is the stuff that I'm really after. So this is iron itself, and it comes out as a liquid because it's very, very hot. The melting point for iron is around about 1,400 degrees, and obviously I've got to be able to move the iron. If it just made a solid of iron, there's not much I can do about it, and there's no way that I can actually move it out of my blast furnace. So the only way I can do that is at 1,400 degrees to melt my iron. Now here's one of the other problems with the iron industry. And there's a product. It's a gaseous product, which is great. It's very, very easy to separate from the liquid because it just bubbles up to the top and leaves. But carbon dioxide, I wonder if you can start thinking about the types of questions which you can expect about CO2. Remember that CO2 itself is actually a greenhouse gas. That means that it's got an ability to trap heat inside the Earth's atmosphere. So CO2, this is a greenhouse gas. I want you to read up a little bit about the greenhouse effect. It's very, very important, and it's leading to climate change all around the world. So the greenhouse gases, these are gases which can trap heat inside the Earth's atmosphere. Please, please, please make sure that you don't actually mix this up with the problems with the ozone layer. Those are completely different gases. So CO2 is a greenhouse gas, meaning that it can trap the heat on the Earth's surface, leading to climate change. And many believe, and there's a lot of evidence for this, that CO2 developed by man's industry is actually changing the climate above us. Okay, now I've put a word down at the bottom of the screen which actually scares a lot of grade 11s and 12s, and that is redox. Let's start taking a look at the redox inside here. What am I actually doing inside this reaction? Well, if you take a look at this reaction, it's actually like a story. I had oxygen which was joined onto iron. They were joined as a compound. Along comes carbon, and carbon decides that it likes the oxygen more than iron. So what it's going to do is it's actually going to steal, it's going to take away that oxygen from iron, and that's exactly what we want to do. Carbon likes oxygen a lot more than iron. What does that mean? It means that carbon is great at taking away the oxygen. Carbon likes to be oxidized. That means that it's a good reducing agent. We're going to talk about these terms in a moment. If you're not absorbing that, that's fine. Just listen, try and absorb as much as you can. So let's just say that again. I've got iron at the moment which is oxidized. It has been treated with oxygen. At the moment, it is in a Fe3+ state. The question is, how do I get it from an Fe3+, so let's actually write it in there. So Fe3+, how do I change Fe3+ all the way to become iron? Well, that's a process called reduction. I'm going to change that charge over there. I'm going to change that 3 plus, which is the charge in the ion, into a 0. I'm going to take away all the charge, and the only way that you can take away pluses is by adding negatives. Let me just repeat that again. The only way to get rid of a positive charge is to add some negative charges. I cannot remove pluses. That means that I'm changing the element. Can't do that, guys. The only thing that you can do is add in electrons to get rid of the pluses. So to change Fe3 plus, I've got to change it into iron over there. Very, very important. Your redox knowledge is absolutely important. That means that iron is in a 3 plus oxidation state. Now, just for interest's sake, the word reduction. So let's actually pay attention to the word reduction. If I take my Fe3 plus and I change it by adding 3 electrons, it does become Fe as a metal. The word reduction actually comes from to change the oxidation state down to a lower level. Reduction means the taking down of or the reducing of. So the lessening of this number over here. So we've gone from 3 plus. So I've got iron in a 3 plus or positive 3 oxidation state. So I'm actually going to write the oxidation number of iron over there. So that's plus 3. When we've got an element, just to remind you about oxidation numbers, elements have got the oxidation number of 0. So I've gone from 3 plus or plus 3, if you're writing it as an oxidation number, I've gone all the way through to 0. I'm sure you'll agree that that is a reduction of that number, and that's where the word actually comes from. So I'm adding these 3 electrons. Now, I've got to start asking myself, where are these 3 electrons actually going to come from? Well, if I'm trying to reduce iron, I need 3 electrons. And the thing to give me the 3 electrons, these come from carbon. So carbon likes to give away its electrons. Why? Because it's a non-metal. So, well, it's a metalloid, so it can behave like either. Carbon is better at giving away its electrons than other non-metals. So if you tried to do this with chlorine, or if you tried to do this with any of the other non-metals, it wouldn't work so well. So carbon, being a metalloid, can behave like a metal by giving away its electrons, and here they are. So these are from carbon. So carbon is giving its electrons. And that is, remember that pure form of carbon, which is called coke. So I've actually taken Fe3 plus, and I've added on 3 electrons, and I've become iron. That's the whole deal behind the iron industry. This is a very profitable industry, and one of the things which led to the Industrial Revolution. Now, if you started taking a look at buildings which were built longer than about 200 years back, you wouldn't find any buildings which were taller than about 2 or 3 stories high. One of the reasons for this is because we didn't have an abundant source of iron and an easy way to make it. The development of blast furnaces powered us through the Industrial Revolution, and that's one of the reasons that we can get these big skyscrapers. Now, just coincidentally, iron actually starts to weaken at certain temperatures, and this is one of the reasons behind the World Trade Center collapse when there were the terrorist attacks in 2001. Iron actually starts to weaken at about 625 degrees. So what you'll find is that iron is not a great idea if you're going to have hot fires inside buildings, which I hope that they're not planning to. Okay, so again, iron is one of the major things which contributes towards very, very, very tall skyscrapers, and it's one of the backbones of most industries. They can actually tell how well a country is doing by how much iron it actually produces. But I think it's almost time for an ad break. What do you think?
I think so too, because it's a lot.
Information bombardment, redox left and right. Okay, so right. So just to sorry, let me just rephrase that again and start speaking English. Okay, so just a reminder of what we've talked about now. I've got iron 3 plus. We're trying to do the reduction all the way down to iron. What I want you guys to do is actually start asking some questions, because I want to make this into an iron section and a redox section. So if you guys have got redox about the iron industry or any of the other mining industries, I actually want to turn this into a little bit of a revision lesson. Maybe you guys can help each other out. What do you think, Ty?
I think so too. That's what I've been saying to the mindsetters. If you see a mindset in trouble, always share your information if you have it. But on that note, mindsetters, make sure, as I keep saying, get on the page, get chatting to us. As Phil said, make sure you have questions. But on that note, we'll see you after this break.